Okay, we're going to use linearization to approximate the fourth root of 260. So the first thing we got to think is, okay, I got to find a value nearby 260 whose fourth root I know. And like I literally just worked it out that we know, or maybe you might not know it immediately, but I'm telling you that the fourth root of 256 is 4. 4 to the fourth power is 256. So that's going to be my starting point, 256. So my A value in my linearization is 256. Then the function value near A will be approximately equal to the linearization at A, which is the function value at A plus the derivative at A times x minus A. And again, in order, like it took me a long time when I was learning calculus to memorize this formula. It took me longer than it should have. This is just the definition of the derivative. Remember, if I move this to the other side, if I write this here as f of x minus f of a is approximately equal to this, and then I divide that guy over, that right there, that's just changing y over changing x is approximately equal to the derivative. That's all this is. That's all we're doing is saying the derivative spits out a slope. It's just the formula for slope. And when we do differentials next, differentials, we're calculating this, the change in y. When we're doing linearization, this guy's on the other side, and we're finding the new y value. That's all we're doing. Okay, so what do I need? I'm going to need the derivative, and I'm going to need the function value at the original, 256, and then the derivative at 256. So f of x, my original function here is x to the 1/4 power. His derivative would be 1/4 x to the negative 3/4. Definitely make sure you understood how I got that. Then f of 256 would be 256 to the 1/4 power, or the cube root of 256. That's 4. F prime at 256 would be 1/4. Okay, let's think about rules of exponents here. That negative means move it down. I'm going to have the fourth root of x cubed. Remember, the bottom is your root, the top is your exponent, because that was a negative exponent. That means put it in the bottom. Or you could do it either way. I could take the root first and then cube it. And a lot of times the arithmetic is easier this way. Oh, sorry, this is f prime of x. So f prime at 256 would be 1/4. The fourth root of 256. Take that answer, cube it, and then multiply by 4. Fourth root of 256 is 4. So I get a 4 cubed there. This is pure coincidence. Literally, this is pure coincidence that this is happening. It was the fact that I had a fourth root and my answer was 4. This is funny. I'm getting 1/4 to the 4, which is 1/256. That's pure coincidence that this number happened to be the same as that number there. Okay, then L of x, I'll write out my linearization is f of a (4) plus the derivative at a, 1 over 256, times x minus 256. That's f of 256. That's f prime at 256. And that's 256. That means the y value on the tangent line when x equals 260, which will be approximately equal to the fourth root of 260, will be 4 plus 1 over 256 times 260 minus 256. That's 4 plus, again, so many 4s in this problem. That difference is 4. Okay, now again, I'm going to get a calculator out to do this. If you lived in the 1700s or the 17th century, and you were Isaac Newton and you had to calculate this, you would just do that by hand. But doing this by hand is a million times easier than doing this by hand. All right, so let's get our calculator out. 4 plus 4 divided by 256. 4.0. 625, I think that's what it was. 625. The actual, so that's my approximation. Actual, to no approximate now, 260, or the fourth root of 260, according to my calculator. So I'll do 260 raised to the 1/4 power. That's how you do a fourth root. So now I'll write all that down. Here, I'm going to move that to my other screen so I can see it and write it. 4.015534273. So if I wanted the error in my approximation, I would just do that minus that. So I don't feel like rewriting all those down again. Top one minus the bottom one. And I'm here, I'll type it out so you can see me type it. So I'm just going to do 4.015625 minus the last answer. So minus second answer. Come on, that's a fantastic approximation. My error is on the order of 9 times 10 to the negative 5th power. So my error is 9.07 times 10 to the negative 5. Okay, that's a good place to stop there.